Welcome friends to the online course titled Risk and Reliability of Offshore Structures. We are talking about lectures on module 1. The focus on module 1, as we already know, is probability and plausible reasoning and introducing reliability in terms of probabilistic estimates. In this lecture, which is lecture 12, we are going to talk about the sampling estimates. We already said the accuracy of reliability or probability of failure essentially depends on how you carefully choose the sampling density function h of x. So, in the last lecture we discussed about the importance of choosing h of x. If h of x, which is the sampling density function, is not carefully chosen, one can land up in a crude method of developing a simulation which may not result in a closer accuracy of estimate of probability of failure. So, h of x also depends upon the random variables which are actually being used, which essentially form the sampling of the whole exercise. Let us now focus on the importance of sampling estimates. We already said our focus is to improve the accuracy of failure estimate. So, obviously, if you really wanted to improve the accuracy of the failure estimate or probability of failure, one should focus on how to improve the efficiency of the simulation method. We have discussed couple of methods in the last lecture. Let us discuss one more method by which an improvement is slightly shown. Let us say an improved technique, an improved approach of simulation is graphically shown here. Try to plot this. Let us say this is U1 and this is U2. We already said to improve the efficiency, so this is my failure envelope, which I call as GU0. I draw a tangent hyperplane to select the design point. So, this helps me now to locate the design point which can be the region of alpha and of course, the value beta minus alpha transpose u should be less than or equal to 0. So, in this estimate, the sampling function is given by h of u phi n phi of beta 0 if beta minus transpose is less than 0. Let me call this equation number 1. In this approach, you will notice that it is very important to estimate u such that a specific condition should be satisfied. So, it is necessary to estimate u such that the following condition is satisfied. So, the condition is u given beta minus transpose u should be less than or equal to 0, equation number 2. Now, let us see how to estimate this u. So, there are different steps involved in this. Let us say step number 1, simulate the standard normal variate ui where I is 1, 2, 3 till n minus 1. In step number 2, simulate the clipped normal variable z. Which can be generated from the probability density function given by f of z is 2 by root 2 pi exponential minus z square by 2 where z is less than or equal to 0. Now, solve for u1 . From the equation z equals, which already I have here, equals beta minus alpha, equation number let us say 3a. On the other hand, un will be given by beta minus z minus summation I equals 1 n minus 1 alpha I ui by alpha I. Question number 4. Interestingly, if the failure domain does not lie entirely in the half space defined by, if the failure domain does not lie within the half space or entirely within the half space, defined by the equation beta minus alpha less than 0, then this approach will also give you a biased estimate of probability failure. Then this approach will give you a biased estimate of probability of failure. So, you have to be careful about this. Now, let us try to plot a typical failure domain generated from this method. So, a typical failure domain generated from this method is shown in this figure. So, that is the design point, and of course, this will remain tangent to the design point at that value, and that is my failure envelope. I can now say so, as usual this is U1 and this is U2 and this is beta, the reliability index, and that is my design point U dash. Of course, the envelope shows it is G of U equal to 0. So, that is the failure envelope which has been improved compared to the earlier failure envelope which you had using tangent hyperplane. So, all these methods are only an improvement on how to actually define the sampling density function properly, so that can land up in a closer estimate of probability of failure. Suppose for example, there are certain conditions. If Ui is less than beta, then the simulation or the sampling will be directed to step number 1. Step number 1, simulate the random variable again. Else, if this condition is not true, then Qi is given by the intensity estimator (1 minus x square m beta square of the value where I is 1 to till where I is a counter, equation number 5, where I is I plus 1, nothing but the counter for the simulation. For every increment, then go to step number 1 to proceed with the simulation. It is important to know the counter will be incremented only under specific condition. The counter should be incremented only when is greater than or equal to beta. At I equals n, we get probability estimate as 1 by n summation of j equals 1 to n Qj, equation number 6, and delta function will be approximately equal to 1 minus probability of failure by n probability of failure, where delta is used to set the target to either stop or to continue the simulation. Equation 6. As we understand, simulation will be terminated when delta is less than delta target. Simulation is terminated. It means that the prescribed maximum number of simulations is reached. It is also adequate if the sampling is done with the normal density at each design point. So, what we mean to understand is at every design point, if the normal density is being used for developing a sampling statistics, then the accuracy of probability of estimate of failure will be better. Let us look this diagrammatically. The whole difficulty is locating the design point. We are trying to get the design point in such a manner that my probability of failure estimate is as accurate as possible and the points of sampling fall within the failure domain. So, now the point is, if I have got many number of design points, let us say I have a design point at the specific location which becomes my failure envelope, and the design point at this location is normal. I call this as, let us say, u2 prime, g2 u0. Similarly, I have one more design point where I have one more failure envelope which is G3U set to 0 and I have a design point U3 prime one more failure envelope which is G1U0 and again I have a design point which I call U1 prime. So, I have got multiple design points now, U2 prime which is normal at this point to this failure envelope, U3 prime which is normal at this design point to this failure envelope, and U1 prime which is normal to this failure envelope which is G1 U0 at U1 prime. So, one should be able to really know if you have got multiple design points like this, how do we actually able to get a good sampling, because one can always land up in either U1, U2 or U3 depending upon what is the failure envelope, and the failure envelope is governed by the choice of your sampling density function h of x. In this case, if you have multiple points, if you have multiple design points, you get m number of limit state surfaces. because every failure surface is a limit state surface. So, in that case the sampling density function h of x is given by a weighted function. I call that as h w u, which is going to be the summation of I equals 1 to m, because there are m failure envelopes or m failure limit state surfaces. So, which is now multiplied by w I h I of u. Call this as equation number 7. Where h I of u, which is the sampling density function, is given by this equation, which is minus half of u minus u y star transpose multiplied by I to minus 1 u minus u y star. The condition is minus alpha less than u less than alpha is the range within which the sampling value of the density function will be chosen. So, equation 8. One can easily see here the above set of equations 7 and 8 gives multivariate normal PDF with mean vector u I star. The above equations lead to multivariate normal PDF. The mean vector of this will be given by u I star and the covariance matrix is I sigma I square. In the whole argument, Wi is called the weighted function. Since I represents a specific count, so it is a weighted function for the ith design point. Now, as you see in this figure, we have many design points u1, u2, u3. So, for every value of the design point, you have to have a weighted function of this. So, Wi is actually the weighted function for ith design point which you have generated. The standard deviation and the weights of this particular equation will be chosen such that now the standard deviation and the weighted function, because that is now the problem, should be chosen such that u and f of x in the failure region are as close as possible. So, one can choose this by trial and error and try to get the proximity as far as possible between the chosen points u and that of f of x. One of the major advantages of this method is that it gives an unbiased estimate, even though this method may not be very efficient as compared to other approaches. The essential reason for this is approximately half of the sample points fall within the safe domain of this method. However, if the failure region is not identified prior to the analysis, this method will indicate the unsuitability with the critical deviation of the coefficient of variation from that of the standard value. So, you get a warning that you are not able to converge, or your sampling points will not lie to the maximum in the failure domain. Having understood this, let us move on to another argument called statistical theories of extreme values. Friends, as we now know and I have learnt, in reliability estimate, parallel systems can also be estimated by use of certain limit distributions known as extreme value distributions. One of the areas of application is to determine the strength of the material under worst combination of loads. Let us say, for example, maximum wind gust, etc. Now, let us consider an example to understand this particular problem. Let us have a system. Let us assume a system S, which consists of n components. This system consists of n components. The system can be an offshore platform. Components can be members of the offshore platform like pontoons, columns, etc. Now, each member or each part of the component or each functionality of the given system may have a different lifetime period. So, let the lifetime of these components be T1, T2, T3, n. There are n components, therefore, there are n time periods. Now, these lifetime values are assumed to be independent. I can give an example. Let us say T1 corresponds to a lifetime period of a drilling derrick, T2 corresponds to lifetime period of a living quarters or the block module of a living quarters, etc. So, obviously, the lifetime period of each one of these components which form a system may not be dependent on each other. So, these lifetime of components are assumed to be independent and identically distributed with the reliability function R of t. So, let R of t be the reliability function with which the lifetime estimates of components are distributed. Please understand that these components are independent of each other. So, all of them put together, because they all form a system, I am not interested in knowing the failure of a component, of course, but I am looking overall the failure of a system. I am looking for probability of failure of the given system. We all know the probability of failure of a given system is dependent closely on the failure components, I agree, but I am not interested in only knowing the probability of failure of a specific component, but I am looking for the influence of the failure of this component on the overall failure of the given system, yes. So, therefore, let T s system be the lifetime of the system. So, T sys is actually given by the minimum 1 less than I less than n of T I. I am also interested in knowing the reliability of the whole system. So, reliability of the system S is given by as a function of time, which will be Rn of T if n tends to infinity. In general, system reliability can be estimated within a given time scale by choosing two sequences such that the sequence of stochastic variables is expressed by a given function. So, one can also choose a time scale of two sequences so that the stochastic variable can be expressed as the stochastic variable can be expressed as T6 minus Bn by An. So, now we will move on to understanding of the sampling statistics, extreme value statistical theories, selection of sampling density function, selection of choice of random variable, choice of simulation methods, and try to apply them slowly on different variables which are going to be responsible for estimating reliability of an offshore structure. So, let us start with environmental loads. Talk about how will you model the environmental loads. Environmental loads act on offshore structures can be classified in different manner. So, there are classification of these forces. One, permanent loads or dead loads. These are called as P class loads. 2, operating or live loads, they are called as L class loads. Third, deformation forces, called as D class loads. Fourth, environmental loads, including earthquake loads, called as E class loads, and lastly accidental loads called as A class loads. So, environmental loads acting on offshore structures can be classified into 5 as given in the blackboard now. Permanent loads of course include time dependent loads as well. For example, gravity loads such as weight of the structure, weight of the permanent installations fall under this category. While this class of loads can be estimated with higher accuracy, characteristic values used to address the associated uncertainties. even though one can believe that P class loads can be estimated with greater accuracy, however, to account for uncertainties in their estimates, one uses characteristic value. The next comes the L class loads, which are live loads. Live loads are generally associated with the nature and the operational features or operational mode of the plant and equipments on the top side. Therefore, one can also choose carefully the characteristic values for live loads, which depends upon the type of structure under consideration. So, depends on type of structure under your consideration. The next comes the deformation class loads, which is called D class loads. D class loads are actually caused by the imposed deformation on the structure, which arise from large displacement. We are talking about compliant type structures which actually result in large displacements because they are designed for large displacements. That is how they alleviate the loads acting upon them. So, these loads may also arise from deformations caused by the temperature difference, differential settlement of the foundation, settlement of support systems that arise in case of structures like articulated towers, triceratops, etc. Because triceratop, we know the deck rests on the ball joints. Therefore, depending upon the M5 characteristic of the ball joint, the top side or the top side settlement can be different, and that can also cause large deformation and displacements to the given system. Therefore, one has to be very careful in choosing the characteristic value prescribed in the design. So, characteristic values prescribed in the design codes should be carefully chosen. It should be the maximum possible value. You must choose the maximum possible value because this value will be associated with a very high degree of uncertainty. So, of course, this is supported by different researchers, Lin 1967, Lin and Kai 2004. So, they advocate that one should choose the maximum possible value of the characteristic values prescribed in the design forces or the design codes, so that they can be associated to take care of the highest possible uncertainties. Now, environmental loads arise from the ocean environment that include wave loads, wind loads, current, earthquakes, ice loads, etc. Each one of them are different events, they have different periods. The mean return period is of course used to account for the characteristic value of this class of loads, because if you come to environmental loads, they include different varieties of loads coming from wave, wind, etc. Each one of them will have a different period. I am interested to know the mean period of this entire class of load, which is rather very difficult to estimate. So, environmental loads or E class loads consists of loads from waves, wind, earthquake, current, etc. Each event can have different periods. I am looking for the mean period of E class loads. It is rather very difficult to find out this. The mean period of course is used to account for the characteristic value of this class of loads. The last one is the external class of loads, A class loads, which are experienced by the platform from different conditions like collision, drop objects, explosion and fire. The characteristic value associated with A class loads should be carefully selected depending upon the subject matter of investigation, operational manner and experience and technology involved in safety and risk assessments. So, therefore, all these kinds of environmental loads or all these kind of class of loads acting on offshore structure can be accounted for representing their degree of uncertainties by using appropriate characteristic values. Obviously, one can easily come to a conclusion that a single characteristic value cannot represent the variation uncertainty on different class of loads. However, as advocated by different researchers, one should use the maximum possible combination of characteristic value because this is useful in accounting for or representing highest degree of uncertainty which are faced by these class of loads in estimating. Now, one can ask me a question, how this will affect the reliability study? Ladies and gentlemen, it is important for us to know that environmental loads or these class of loads, one of the important input which is going to cause failure to my system, yes. So, if I am not able to estimate the input loads in a proper manner or I am not able to account the uncertainties associated with these loads, my estimated probability of failure of the system, yes, may not be accurate. So, one should have enough knowledge and carefully choose characteristic values associated with each class of loads as advocated by the design codes. So, a variety of uncertainties arise in all class of loads. Characteristic values of course are used to account for these uncertainties as given by Maddox and Wildenstein. So, in this lecture we started introducing you to understand the importance of sampling density function. We also said something about the sampling theories of extreme values. We are now moving towards understanding the estimates of input which are going to govern the probability of failure of offshore structures. We started with discussing environmental loads. We will take you forward to understand this. Once we complete this discussion, we will take you back to the reliability theories and then we will apply this knowledge of plausible reasoning and probability theory to that of reliability estimates in the second module. Thank you very much.